All right, folks, here we go. Today's lecture for you is going to be on Newton's second law. Hopefully, you've taken a few minutes there to be able to go through and get that first law question stuff done. Okay. So what we're going to do is we're going to start running this thing here. Okay. Some terms for you to write down first and foremost. All right. So take some time, write these down. If we need to pause the screen, we can, just for you to get them all. Force of gravity, F of gravity. This is the one that we've seen quite often now, and we've talked a little bit about as a force that points to the center of Earth, meaning that this is the one that you experience from day one. This is the one that will keep us going towards the kind of ground, so to speak. Doesn't matter if we're here or if we're in Australia, it's going to pull us towards the center of the Earth. Next one. Excuse me. Force friction. Force that opposes motion. So this is the one, if you've ever gone on the sidewalks, right, when they're icy and try to slide, and all of a sudden you hit the cement, and the force of friction on the cement and the ice are completely different, right? The ice is going to let you slide for a long, long time, whereas the cement, what it's going to do is it's eventually going to stop you, and it's going to slow you down and cause you to sometimes even trip, right? Static friction, that's stationary friction that keeps an object in place. What we mean by this is if you think about trying to push a desk or trying to push, like a box or something like that, right? The static friction is the friction between the box or the desk and the ground that doesn't allow you necessarily to move it, right? Once you overcome that, once you get it to actually start to move, then what we're going to see is we're going to see actual movement, all right? Kinetic friction, moving friction that slows an object down. So when you're out riding your bike or when you're out riding a skateboard or a scooter or in your car, whatever it may be, as soon as you stop trying to accelerate, as soon as you stop trying to work forward, what ends up happening is this kinetic friction is the friction between the wheels and the surface that you're on, right? And that all of a sudden starts to slow you down. Now, I remember very vividly, driving on loose sand one time on kind of a back road type of place, and all of a sudden I felt myself starting to slide a little bit, so I took my foot off the gas, right? That loose sand slowed me down way faster than any blacktop or any concrete that we could have. Sorry, there's spelling. You got to stay here, though. Force of tension. Force of tension is a force that is used to pull with. Typically, when we talk about tension, this is a rope, this is a wire, this is a string, right? So if you're up on Buck Hill and you're using the rope climb that they got on one of those hills, right? The force of tension is going to be the one that's going to basically pull you up. As soon as you grab onto that rope, it's going to start to pull you up, right? The other way you can look at that is if you're playing tug of war, right? You get your hand wrapped around that. That's going to be used to pull you that way as well. Okay. So if we drop a bowling ball and we drop a feather from 20 feet, which will hit first? Well, yeah, you're correct. Bowling ball should hit first, right? So when we look at this, what we should be able to see is that, let me try and get this pen here. Sorry. So what we should be able to see, there it is that bowling ball should hit first, okay? So the forces that are at play, we got gravity pulling down there, we got gravity pulling down there, right? Now, this one is going to have a little bit of air resistance pushing up. This one is going to have a lot of bit of air resistance, right? The construction of the feather, the evolution of the feather makes it so that when we look at this object here, what we're going to see is that this thing is going to cause that air to basically catch it. So when this thing hits, the air resistance should be pretty great. Now, the gravitational pull on both of these should be the same. Gravity doesn't pull down on stuff harder just because it's a bowling ball or it's a feather, right? You can even ask that age-old trick, which weighs more, a pound of feathers or a pound of gold? Well, they're both a pound, so they both weigh the same thing, right? So then we go to a vacuum. Now, a vacuum means no air, all right? So if we've got no air, it would be like the equivalent of basically saying, hey, we're going to take this room, we're going to seal it up, we're going to pull out all the air out of here, right? It'd take a bit for that to happen. That's also not great for us because as human beings, we've kind of grown up with air resistance around us. One, to breathe, and then two, just because that's kind of what our skin is used to pushing against, is this concept of air, right? So no air is actually going to cause the water in our body to start to kind of evaporate a little bit. Not a great thing, mind you, right? So if we look at this now, this one will still experience gravity down now, and this one will still experience gravity down, right? But without air, the design of the feather, all of these nice little fluffy edges that it has here, all of those designs become useless without air. Just like all of the aerodynamics of this bowling ball become useless. So what should happen is we should see that both of these hit at exactly the same time. Okay. So now what I'm going to have myself do is I'm going to have him pause the video, right? And then you're going to check out this video, which is pretty gnarly. Okay. So you're going to watch that one. It'll take you a few minutes to do. So open up a new tab, and then that thing's going to be right there for you. Okay. All right. Balanced versus unbalanced forces. When we look at balanced versus unbalanced forces, an object will experience balanced forces if you're standing still, right? So you're standing here. I know, super high-tech drawing. Shut it. Right? Balanced forces, down and up. Gravity and whatever surface is pushing against it, right? Because we're not moving, because there is no acceleration forward, right? Because this doesn't exist, we don't have any force going that way, right? Moving at a constant velocity. This one's always weird for people, right? So if I'm going forward at a constant velocity, what ends up happening is that these two forces, meaning my push forward and the whatever air friction between the surface pushing backwards, that's going to balance each other out, right? So constant velocity just means, hey, I'm setting my cruise control, right? I'm going at 20 miles an hour, and all I'm doing is I'm keeping going 20 miles an hour. If I stay 20 miles an hour and 5 seconds later I'm going 20 miles an hour, guess what? I don't have any acceleration. No acceleration means no force. It means that we're balanced as far as that's concerned, okay? If an object experiences an unbalanced force, it will always be accelerating, right? So if all of a sudden, say, I'm pushing forward and I got a little bit of air resistance, right? Now I'm going to keep going faster and faster and faster until I can, right? Or say that, hey, the only force is this backwards force. Well, from the wind, like I'm not actually pushing the gas pedal, I'm just coasting. Well, then all of a sudden now I'm going to start to slow down. So its speed should be constantly increasing, or its speed should be constantly decreasing. Increasing, decreasing. Okay? So then, if we look at this person, right, sitting on a desk, what are the forces acting on the person? Well, first one down is gravity, right? And then what we've got is we've got the chair pushing up. So the question for you folks is, are these forces balanced? Meaning right now when you're sitting in your desks, right, are these forces balanced? Because are you falling? Are you accelerating towards the ground? Or are you just kind of stationary there? The hope is that you're all stationary there, right? If you're doing the slowest fall ever, that's going to be kind of tough. You know what I mean? That's going to be kind of bad for us. All right? So in this case, what we should see is our forces are balanced because we're not actually accelerating. If I go ahead and pull the chair out from underneath you, right? Boom, gravity going down. Now what should be holding me up is just this little bit of air here, right? I no longer have the chair to be able to hold me up anymore. So now I've just got a little bit of air pushing up against me. In this case, what should happen is I should be falling, right? I'm going to be falling towards the ground. As I fall towards the ground, right, that air just can't exert enough force to balance me out. This would be an unbalanced, all right? That's what we would see in this case here. How about here, right? So we got the force down the hill. Likely now, for those of us who've gone sledding, we know that the force between this kind of rail of the sled and the actual snow itself is probably minimal, right? So in this case, we should see an unbalanced force, right? This person should be moving down the hill. As they get further down, once they get down to here, folks, man, that's going to be really unbalanced, right? Because we're really going to start to accelerate even faster, 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 okay? force of tension here on this old boy, right? So what we see is he's trying to pull back up this way. The fish or whatever is in there is pulling that way. We see that his force of tension isn't great enough. And so what ends up happening is that we see this is an unbalanced force, right? Old boy's going to fall into the water, get pulled, whatever may happen there. Okay? Unbalanced force, this is what we call fun. All right? So unbalanced force, we just take the UN and write it right below that force there. All right? So unbalanced force causes the mass to accelerate. So what we're going to see is fun is our unbalanced force, M is our mass, and A is our acceleration. Okay? So make sure you take some time. Just write that down quick as a formula that's going to be important for us. Right? So, fun equals ma. Once we have that unbalanced force, that's going to be equal to a mass times acceleration. Like we talked about with that force of tension, right? Old boy was starting to accelerate into the water. The sled was starting to accelerate down the hill, right? So what we see is, here's our triangle. This fun part up on top, that's going to be in newtons, right? Mass has got to be in kilograms. Acceleration, meters per second per second. Okay? So make sure you write that down. Make sure that you take some time with that one, and make sure that you remember when we're doing this now, right? We're going to divide across the top like this. So if I get an unbalanced force and I get a mass, I'm going to take fun divided by mass. If I get an unbalanced force and I get an acceleration, I'm going to divide those two as well, right? If I get a mass and an acceleration, I'm going to multiply those two together. Forces, again, after Sir Isaac himself, are going to be measured in newtons. Masses are going to be kilograms. And then acceleration is just meters per second per second. Okay? At this point in time, you should have enough information to be able to work through homework stuff. Reminder, be respectful. And we will talk to you folks tomorrow when we do lab. All right? Have a great rest of your day. Take care. Bye.